Jai Hind students, myself Dr. Meenakshi Sinha. I am Assistant Professor in Applied Science and Humanities Department, Ajay Kumar Garg, Engineering College, Ghaziabad. Today I am here to give the video lecture for the course Engineering Mathematics 1 with subject code BAS 103. So the concept which I am taking over here is from the unit 2nd, which is Differential Calculus 1, and the subtopics are Leibnitz theorem to find out the nth derivative at x equal to 0 and example based on Leibnitz theorem. So first of all, what is the meaning Leibniz theorem? Leibniz theorem is a very important concept for the differential calculus, and this Leibniz theorem gives you to find out the nth derivative for the product of two functions of x. So first, coming to the statement of the theorem, states that if u and v are two functions of x, then nth derivative of the product of u and v with respect to x is given by. Look at the statement, if dnv means the nth derivative of u into v is nc0 nth derivative of u into the second function v as it is plus nc1 n minus 1th derivative of u into derivative of v plus nc2 n minus 2th derivative of u into d square v plus ncr n minus rth derivative of u into drv means rth derivative of v, and going up to the nth term it's ncn u as it is into nth derivative of v. What we do over here, that out of this u and v, one of the function is taken as the first function and the second one as the second function. So if I look at the statement, what the statement means, first we start with the nth derivative of the first function into second function as it is plus nc1, the lower order derivative to this n means the n minus 1th derivative of u into the first derivative of the second function v plus nc2 n minus 2th derivative of u into the second derivative of v, and so on. What we are doing here, the first function which we have taken as u, we started with its nth order derivative and we go on decreasing its order in the successive terms. Similar, v we have taken as the second term, second value, and its order of derivative we go on increasing in successive terms. So this is the statement of Leibniz theorem. If I look at this, so if I now expand this nc1, nc2, ncr, so what are these nc1, nc2, ncr? They are nothing but, if you remember the value, ncr is nothing but n factorial by r factorial into n minus r factorial. So if I start putting r equal to 1 over here, so what will become this? If I now just look at, if I want to find out the value nc1 from here, this will become nothing n factorial by 1 factorial into n minus 1 factorial, and which is nothing but equal to the value n. So nc1 replaced with the value n, nc2 is n into n minus 1 by factorial 2, nc3 n minus 1 n minus 2 by factorial 3, and so on. So this is the Leibniz is also written in this form. This is also another way for writing the Leibniz theorem. Okay. So just directly I am coming to the examples. Like the first example says that find nth derivative of e to the power 2x into x square. How we first find out that we have to apply Leibniz here, because it's the product of two functions of x and these two functions are of different nature, means e to the power 2x is an exponential function and x square is an algebraic function. So we start differentiating this by Leibniz theorem and we differentiate it n times. What we get, d to the power n of e to the power x into x square. Now look at how we apply the Leibniz over here. If you remember the statement which we have discussed in the last slide, my statement says that if I write over here that nth derivative of product of two functions u into v is nothing but starting with the nth derivative of the first function u into the second function v as it is plus nc1 n minus 1th derivative of the first function u into the first derivative of the second function v, and so on, nc2 n minus 2th derivative of the first function u and second derivative of v, and so on. So in this process, any of these two functions we have to take as the first function and the second one obviously the second function. So please remember, the second function is that function we will take whose derivative will terminate after some derivatives. If I look at that, x square is that function whose the first derivative is 2x, the second derivative is 2, and the third derivative becomes 0. So this x square is taken here, the second function v, and obviously this e to the power 2x will become then the first function u. Yeah. So now I apply my Leibniz over here. Look at what we get. The theorem says that we have to take the nth derivative of u. So I write it like nth derivative of the first function e to the power 2x into the second function v, which is x square as it is, plus what the next term, nc1. nc1 is nothing but n into the lower order derivative, means n minus 1th order derivative of e ki power 2x into first derivative of x square. First derivative of x square, we know that it's 2x, plus nc2. nc2 is n into n minus 1 by factorial 2 into n minus 2th derivative of e to the power 2x into the second derivative of v, and 2x derivative is nothing but 2. And if I think about the next derivative of 2, that is 0, means Leibniz theorem for this process stop here for this function. Now look at what is the value of this nth derivative of e to the power 2x. So if you remember the successive differentiation, so in the successive differentiation we know that the nth derivative of e to the power ax is nothing but given by a to the power n into e to the power ax. So by this process, if I start writing the nth derivative for e to the power, this will become 2 to the power n into e to the power 2x into the function x square, plus n minus 1th derivative of e ki power 2x, n replaced here with n minus 1. So what happened, plus n as it is, this will become 2 to the power n minus 1 into e to the power 2x into 2x as it is, plus the next term n minus 1 by factorial 2. The n minus 2th may what happened, this will become 2 to the power n minus 2 into e to the power 2x into 2, and this 2 cancel with this 2 over here. Okay. So finally, if I look at the statement, what we are getting something like, look at 2 to the power n e to the power 2x into x square, which is this first term. Next one, n into e to the power 2x, this 2 combines with this 2, making the power of 2 as 2 to the power n. So it's n 2 to the power n e to the power 2x into x, and x 2 to the power n into e to the power 2x, the second term. And the third term, we have n minus 1 2 to the power n minus 2 into e to the power 2x. So that's how we apply the Leibniz theorem for product of two functions of x. This is the formula over here. Any of these two, we have to take the second function. Second function is always taken as that function whose derivative will terminate after some step, whose derivative becomes 0 after some step. Yeah. So look at some other example. The next example is this: if y equal to x to the power n log x, then prove that yn plus 1 is factorial n upon x. So look here, I need to find out the n plus 1th order derivative, and we know that Leibniz theorem gives me only the nth derivative. Means to go up to the n plus 1th derivative, what we have to do? First we calculate the first derivative and get the value y1, and after getting this y1, then we apply the Leibniz theorem, we get the nth derivative, and nth derivative of y1 is nothing but yn plus 1. So we get this relation like this one. Clear? So we start with the question, y given here is x to the power n log x. Starting with y1, apply the product rule here. First function x ki power n as it is into derivative of log x is 1 by x, plus derivative x ki power n is nx n minus 1 into the second function log x as it is. So what we do next? We take the LCM for this x over here. Taking its LCM, this will become x into y1 equal to x to the power n, and this x combined over here, I write it like, look at, this will implies, taking the LCM, we get x into y1 is equal to x to the power n plus n into x to the power n log x. And what is this x to the power n log x? This is nothing but the given function y. So in place of this x to the power n log x, we are replacing the value y over here. We are replacing the value y over here. Clear? So now in the next step, we apply the Leibnitz theorem to find out the nth derivative for this expression. Look at how we apply the Leibnitz. So first we are applying the Leibnitz for this first pair. So out of this x and y, any of these function, we have to take the second function, and second function, the rule for choosing the second function, whose derivative will terminate after some step. We've seen that x here is taken as the second function v, and this y1 is taken as the first function u. So applying the Leibniz over here, what my Leibniz theorem says, nth derivative of first function, and we know that if I take the nth derivative of y1 is already here, the nth derivative of y1 is yn plus 1 into the second function x as it is plus, what next, nc1, its lower order derivative, n minus 1th order derivative. So n minus 1th to this is, its lower order is yn into first derivative of x. Its first derivative is 1 and next derivative of 1 becomes 0. So here the Leibniz theorem will stop. Coming to the right hand side part, now I have to take the nth derivative for this x to the power n. So if you remember again in successive differentiation, if I need to find out the nth derivative for x to the power n. So if I start differentiating this, like the first derivative is nothing but nx n minus 1, second derivative n minus 1 x to the power n, and going like the same, the nth derivative is nothing but given by the value factorial n. So putting this value over here, its nth derivative become factorial n, and for this n into y, n is a constant here and derivative of y nth is yn. So what happened? Writing this again, is nothing but yn plus 1 into x, nc1 is n into yn is equal to factorial n plus n into yn. This n into yn will cancel out, giving you the result that yn plus 1 is equal to factorial n by x. So we are getting yn plus 1 is equal to factorial n by x. This is how we apply the Leibniz theorem to prove this result. Yeah. So coming to one more example, look at if y equal to log x plus under root 1 plus x square whole square, prove that yn plus 2 into 1 plus x square plus 2n plus 1 x into yn plus 1 plus n square yn equal to 0. Yeah. So y is given a function of x, we have to go up to the n plus 2th derivative. And we again know that Leibniz theorem gives me only the nth derivative. So what we start with? We start calculating the first derivative y1, then the second derivative y2, and after getting the statement for y2, then we apply the Leibniz theorem to get yn. Yeah. So what we start? We start with the statement, we start with the question, y equal to log x plus under root 1 plus x square whole square. So if I write down the y1 over here, I am solving over here, I write down the first derivative y1. So first taking the whole square is 2 log x plus under root 1 plus x square into derivative of log function, which is 1 upon x plus under root 1 plus x square into derivative of this function of x, which is 1 plus 1 by 2 under root 1 plus x square into 2x. So this is the derivative of y, which is this long expression. Now what happened? This 2 will cancel out from here, taking the LCM over here. We write it like twice log x plus under root 1 plus x square, and here this is in denominator, this will become coming like this, x plus under root 1 plus x square, and taking the LCM over here, this is also under root 1 plus x square plus x divided by under root 1 plus x square. Now if you look at what happened, this value will cancel out, and this under root 1 plus x square, but this is your y1. This under root 1 plus x square, what is this? This is shifted on the left hand side part, means this is the rule ki if on writing y1, you are getting something in the denominator of the right hand side. So that denominator function of x must be shifted to the left hand side part. And if that denominator contains under root sign, So to remove that under root sign, we have to do the squaring also. So what we do, we shift this under root 1 plus x square to the left hand side, writing this as under root 1 plus x square into y1. And what we get over here, it's 2 log x plus under root 1 plus x square. This 2 log x plus under root 1 plus x square. And to remove this under root sign, we are doing the squaring both sides. So when we do the squaring both sides, this will become 1 plus x square. This will become y1 square is equal to 2 to the 4 into log of x plus under root 1 plus x square ka whole square. And what is this log x plus 1 plus x whole square? If I look at that, if this is nothing but equal to the given function y. So in y1, in calculating y1, we try to write down the right hand side as the function of y. So this is nothing but written as equal to 4y. So this is the expression we are getting, that y1 square into 1 plus x square equal to 4y. This is the process of getting it. Yeah. So after that, we have calculated now the value y1. What is the next step? Next step is to obtain the value y2, means we differentiate this again to get the expression y2. Coming to the next slide. This step we have get in the last slide, y1 square into 1 plus x square equal to 4y. We differentiate it again. So for this derivative, we have to apply the product rule. Apply the product rule here. First function 1 plus x square as it is into the y1 square derivative is 2y1 into derivative of y1, which is y2, 2y1 y2, plus the second function y1 square as it is into 1 plus x square derivative is 2x, and derivative of 4y is nothing but 4y1. The first derivative of y is y1. Clear? So what happened here? If I look at this 2y1 is common in each, so we can cancel this 2y1 from each term. Here also the 2 and y1 will cancel out. So what we left with? We left with the value y2 into 1 plus x square plus x into y1, and shifting this plus 2 over here, minus 2 equal to 0. So this is the expression for y2, and after this now we apply the Leibnitz theorem to obtain its nth derivative, because we know that nth derivative for y2 will become yn plus 2. This one. Clear? So now we apply the Leibnitz theorem. Now look at how we apply the Leibnitz over here. Coming to the first pair of values. The first pair of value here is y2 into 1 plus x square. Yeah. I am writing this expression again. I write this is y2 1 plus x square plus x into y1 minus 2 equal to 0. So now first I am taking the first pair of value. Out of this y2 and 1 plus x square, we know that which function is taken as the second function, whose derivative will become 0 after some step. So it's seen over here that this 1 plus x square is the function which is taken as the second function v here, and y2 is taken as the first function u over here. This is the first step to identify u and v. Yeah. Now taking the Leibniz theorem, apply the Leibniz theorem to get the nth derivative. Look at what we get. Leibniz theorem says that nth derivative of first function. What is the nth derivative of y2? It's yn plus 2. Because y2 is already there, nth more will give you the value yn plus 2 into second function as it is, 1 plus x square as it is. What the next? nc1. First function, one lower derivative, one lower order derivative. So the next lower order to yn plus 2 is yn plus 1. Just subtract 1 from here, I get the value yn plus 1. What next? Into the first derivative of 1 plus x square. The first derivative of 1 plus x square is 2x, plus next one is nc2. The next lower to yn plus 1, lower to yn plus 1 is yn into next higher to 2x. So one more order derivative for 2x is 2, and when I think about the next derivative for 2, that is 0. Means this is the Leibniz for only this first pair of values. Coming to the second pair, this is x into y1. I think this is clear to you all that now x is taken here as the function v and y here is taken as the first function u. So starting with Leibniz, look at what we write. Nth derivative of first function, nth derivative of y1 is yn plus 1 into the second function x as it is, plus next is nc1. one lower order derivative to yn plus 1, which is yn, into the higher order derivative to x, which is 1, and one next derivative is 0. So here it stops. Coming to the next term, which is a constant 2, and the derivative of constant 2 is 0. So this is stopped here, this I write it equal to 0. Now just writing the next step, but we get, look at, it's 1 plus x square yn plus 2 plus nc1, we know that this is n into 2x yn plus 1, nc2 we know that it's n minus 1 by factorial 2 into yn into 2, and this 2 will cancel out like this, plus the next term is yn plus 1 into x, nc1 is nothing but n into yn equal to 0. So after writing this, the last step is to just combine the coefficients of yn plus 2, yn plus 1 and yn. So just combining their coefficients, look at yn plus 2, we have only single term. So we are getting just 1 plus x square into yn plus 2 plus. If we look at yn plus 1, one is this term, this is 2nx, and one is this term plus x into yn plus 1. Last bracket is for the coefficient of yn, this is yn, this is n square minus n, and this is also yn plus n into yn equal to 0. This plus n minus n cancel out, and if we look at the last result, the result is same, it's 1 plus x square yn plus 2 plus x, we can take common outside, it's 2n plus 1 x into yn plus 1 plus n square into yn equal to 0. So that's how we apply the Leibniz theorem for this type of, means ki if you have to go up to yn plus 2, so your process is that you calculate first y1, then the second derivative y2, and after getting the expression for y2, next we apply the Leibniz theorem to get the n derivative, this one. Yeah. The next I am coming to one important application of Leibniz theorem, that up to Leibniz we get the nth derivative. So determination of nth derivative of the function at the point x equal to 0, means you have to find out the value for yn 0. Yn 0 is nothing but the value of yn at the point x equal to 0, because yn is the function of x, like this one. So what is the working procedure to find out the value yn 0? Look at, if I look at in this, the first two steps are same which we are doing over here. Like for the given function y equal to fx, find y1 and y2, find the first and second derivative. Apply Leibniz theorem to find out the nth derivative, like this one. They are same as we are doing in the previous slides. Look at what we have to do in the third slide. Put x equal to 0 to obtain y0, y1 0, y2 0 and yn plus 2 0, means in the expressions where we have written y1, y2 and yn plus 2, just in all these four relations, just you put x equal to 0. What the next step? Put n equal to 1, 2, 3 and 4 and so on in the last equation of step. Last equation of step 4 means this equation. So in this equation we give various values to n, starting with n equal to 1, 2, 3, 4 and so on, and discuss two cases for n odd and n even. Means we have to show two cases. One for n to be odd, means when n is taking the values here 1, 3, 5, 7 and so on. Second, we have to discuss the case when n even, means n is 2, 4, 6, 8 and so on. This we will see in the examples. So this is one of the application, you can say, that of Leibniz theorem, that by doing the Leibniz we able to find out the nth derivative of the function at x equal to 0 also. Yeah. So now look at the example of this. The first example, if y equal to sine m sine inverse x, then find yn 0. Yeah. So according to our process, what we start with, we have provided with the value y equal to sine m sine inverse x, means now in all the steps we keep on putting x equal to 0 to obtain our required values. So here when I put x equal to 0, look at, this will become sine 0, and we know that sine 0 is nothing but 0. So means the value of y0 we are getting equal to 0, the first one. What we do next? Find out the first derivative y1. Okay. start finding the y1 value. Now we start differentiating this. If I write over here, y is the value sine m sine inverse x. So start calculating the y1 value. First the derivative of sine theta. Sine theta derivative is cos theta. It's cos m sine inverse x into derivative of this m sine inverse x. We know that its derivative is m is a constant upon under root 1 minus x square. So this is the derivative. Now we know that according to our rule, what we need to do? We have to do two processes. One is, if we have something in denominator on the right hand side, we need to shift it to the left hand side. Second, if that term is in under root, so we do squaring also to remove that under root sign. And third one, we try to write the right hand side part as a function of y again, in terms of y again. So doing this whole process, first we are shifting this under root 1 minus x square to left hand side. This will become y1 under root 1 minus x square equal to m cos m sine inverse x. To remove this under root, what we have done, we have squaring both sides. Just do the squaring. We get y1 square, 1 minus x square is equal to m square cos square m sine inverse x. Yeah. And we know that, but I write this further as, I write this as m square into 1 minus sine square m sine inverse x. All of you know that sine square theta plus cos square theta is always 1. All of us know that sine square theta plus cos square theta is always 1. So writing this as 1 minus, and sine square m sine inverse x is nothing but y square. So putting the value y square, so this we get the equation y1 square into 1 minus x square equal to m square into 1 minus y square. This one. Clear? Now, when we have calculated y1 in the first step, here again you put x equal to 0 to get the value y1 0. When I put x equal to 0, look at what happened. This will become 0, this will become 1. When I put x equal to 0 here, you know that cos 0 is 1, and what is the value here? M. So y1 0 is nothing but we are getting the value as m. So what we are getting, that y0 is 0 and y1 0 is m. So after getting this expression, what is the next step? We differentiate it again to get y2. So again differentiating it. Look at, again we start differentiating it. So differentiate it in the left hand side. We apply the product rule, 1 minus x square as it is into derivative of y1 square. It's 2y1 into derivative of y1, which is y2. 2y1 y2 is equal to m square, sorry, minus derivative of 1 minus x square, which is minus 2x into the second function y1 square as it is. On the right hand side, it's m square. This is a constant. Derivative of minus y square is minus 2y into derivative of y, which is y1, minus 2y y1. Yeah. What happened again? 2y1 we can cancel out from each term. 2y1 is common over here also, common over here also, and this is cancelled from this term also. Look at what we left with. We left with 1 minus x square y2 minus x into y1 plus m square y equal to 0. And here again, if I put x equal to 0, so look at what we get. This gives the value x equal to 0 will become 1. So this is the value y2 0. X equal to 0 is 0. Sorry. And this will go on the right hand side. This is minus m square y0. And if I look at the y0 value, the y0 value we have calculated is 0. So using this value over here, I can write that this is equation number 1. If I say, so I say that using equation 1, I say that y2 0 is also equal to 0. Yeah. So what we have calculated, we calculated that y0 is 0, y1 0 is m, and y2 0 is also 0. What we do next? Now we have calculated up to the second derivative y2. So next step we have to apply the Leibnitz theorem to get the nth derivative over here. Yeah. So look at, apply Leibnitz theorem n times to get the nth derivative of this expression, which is y2. Now start differentiating this. Taking the first pair, y2 into 1 minus x square. I think this is clear to you all that this function is taken as v now, this is taken as u, the first function over here. Applying the Leibnitz, nth derivative of y2, nth derivative of y2 is nothing but yn plus 2 into the second function 1 minus x squared as it is, plus nc1, its one lower order is yn plus 1 into its higher order, first derivative is minus 2x, plus nc2, it's one more lower order to yn plus 1 is yn into its next derivative, which is minus 2, and the next to minus 2 is 0. So here the Leibniz for this first pair is completed. Coming to the second pair, xy1. Now here also this x is taken as v, this y1 is taken as u. So apply the Leibniz for this pair, and the derivative of y1, it's yn plus 1 into the second function x as it is, plus nc1, one lower to yn plus 1 is yn, and one higher to x derivative is 1, and next order derivative to 1 is 0. So here it's completed. Coming to the last term, now this m square y, m square is a constant, and nth derivative of y, you know that it's simply yn. So writing this as plus m square yn equal to 0, this is the value. So this we have applied the Leibniz. Now just we need to solve it, put the value nc1, nc2 and just expand it. I get the value, this is 1 minus x square yn plus 2 plus nc1, we know that it's n yn plus 1, and this is minus 2x, plus nc2, we know that n minus 1 by factorial 2 into yn into minus 2. Next value is minus x into yn plus 1 minus nc1 is written as n into yn plus m square into yn equal to 0. This 2 will cancel out from here. Now just we need to combine the coefficients of yn plus 2, yn plus 1 and yn. So yn plus 2 we have only single term, writing like this 1 minus x square yn plus 2 in the second bracket. Look, we need to combine the coefficients of yn plus 1. So here it's minus 2nx and here it's minus x into yn plus 1 we have taken common out. The last bracket is for the coefficients of yn. Look at this is yn. So the first coefficient is n square minus n. This is also yn minus n. And this is also yn plus m square. I think this is somewhere wrong over here. If I multiply this over here, this is minus n. Okay, sorry, this is minus 2. So this minus will be used over here, writing this as minus n square plus n. Such that this plus n and minus n will cancel out into yn equal to 0. So what the final result? It's 1 minus x square yn plus 2 minus, we have taken common outside and x also common. So minus 2n plus 1 x into yn plus 1, and from here what we are getting? Plus m square minus n square into yn equal to 0. So look at the last result, we are getting the same yn plus 2 into 1 minus x square minus 2n plus 1 x into yn plus 1 minus n square minus m square equal to 0. We erase it. Yeah, this is the result. So now, what we need to find? We need to find out the value at x equal to 0. Now what we do next? We put x equal to 0 in this expression. So when putting x equal to 0, what we get? This is 1. So this is yn plus 2 0. X equal to 0 gives you this equal to 0, and n square minus m square, this will become yn 0. So this is my last expression for getting the yn plus 2 0 value, and this type of relation is known as recurrence relation. This type of relation are known as recurrence relation. Yeah. So now coming to the next one, now what we need to find, we need to find out the value of yn at x equal to 0. So we have write down all the values which we have computed. We look at that y0 is 0, we look at that y10 is m, y20 is 0, and this is the recurrence relation, yn plus 2 0 is equal to n square minus m square into yn 0. This is the value. Clear? So this is my recurrence relation. Now I start putting various values of n over here, and now I break these values of n into n odd values and taking the n even values. We generally put a line in between. Here we take the values n for odd like 1, 3, 5, 7 and so on. And here we take only the even values like 2, 4, 6 and so on. Now look at what happened. We are putting these values of n in this last relation, which is the recurrence relation. Put n equal to 1 over here. Look at what we get. 1 plus 2 is 3. We are getting on the left hand side the value y30. Put n equal to 1 over here. What we get? 1 square minus m square. Put n equal to 1. This is y10. And y10 we already calculated. What is the value y10? It's m. So putting the value y10 over here, so nothing but m into 1 square minus m square. So this is the first value which is we have calculated from the recurrence relation, which is y30. What next? Put the next value n equal to 3 in this relation. Putting n equal to 3 gives me here y50. What is this? Putting n equal to 3, this is 3 square minus m square, n equal to 3, this is y30. And from where we get this y30? We have already calculated this y30 in the last step. Put it value over here. So this will become m, I am writing in the beginning, this is 1 square minus m square into 3 square minus m square. So this is the value for y50. This is the value of y50. Similar next we put, if I put n equal to 5, so what I get the value y70 over here. And in which term we are getting the y70? In terms of y50. y50 I have already calculated. I again put this value in that y70 and write down the y70 over there. So here I am getting a symmetry to write down the value yn0. How we get yn0? Means by symmetry. If I now try to write down the value yn0, look at what I get. M is repeated. If you look at this, M is repeated in each of the value y1 also, y3 also, y5 also. So this M must be here in yn also. But the second term which is repeating, 1 square minus m square, here also it's 1 square minus m square, and in y7 also it's 1 square. So here also it's 1 square minus m square. But the next term, it's 3 square minus m square. And can you think where up to which term this will go? Look at how we make the symmetry. For y50 we have written here 3 square. For y30 we have written here 1 square. So can you think what we write for yn0? 3 is nothing but 5 minus 2. 1 is nothing but 3 minus 2. So for the nth derivative we write this as n minus 2 square minus m square. So this is the nth derivative for which values? For n to be odd values, when n is taking the odd values. Similar, we are taking the case when n is even. Start putting. We put n equal to 2 over here. But we get 2 plus 2, 4. We are getting the y40 equal to. Put n equal to 2. So this is 2 square minus m square. On the right hand side we get y20. y20 we have already calculated. The value y20 is 0. Put this value over here. So this coming out to be equal to 0. So y40 is also 0. Because it depends upon the value of y20, which is 0. Next put n equal to 4. So we get y60. What will become y60 when I put n equal to 4? So this will become 4 square minus m square into y40. And what is y40? We have just calculated, it's 0. So y60 is also 0, and based on this symmetry, if I try to write down the value yn0, so that is also equal to 0. Means for n to be even values, when n is taken even values, the nth derivative at x equal to 0 is equal to 0, is taking the value 0. In last, just we combine all these values and we finally write down that the value I am writing over here, that the value yn at x equal to 0. What is this? We write in the curly bracket for various values of n. First I am writing for n odd. So n odd, it's taking the value m 1 square minus m square, it's 3 square minus m square, and going up to n minus 2 square minus m square, and this is the value for n taking the odd values, when n is taking the odd values. Next we write down the second bracket. If n is taking the even values, we are getting the value as 0 when n is even, like this one, when n is even. Yeah. So this is the final value yn 0 for n odd and n even, and this is the process ki how using the Leibniz theorem we get the value of the nth derivative at the point x equal to 0. Yeah. So this is one important application of Leibniz theorem, and Leibniz theorem itself is very important to find out the nth derivative for the product of two functions of x. Thank you. Find out the derivative, nth derivative of two functions of x. Similarly, you can do the any other example also. Means if I do this example, y is equal to e to the power m cos inverse x, find yn 0. In this also, we have calculated like y0 e to the power m pi by 2. We have calculated y1 by the same process, y1 0 minus m e to the power m pi by 2. The value y2 0, which is m square e to the power m pi by 2. And by Leibniz theorem, we calculated yn plus 2 0, which is n square plus m square into yn 0. Clear? So after getting all these values, finally when we start finding the value yn 0, because all you know how we find out up to the Leibniz theorem. Clear? So when you start finding, here also we divide this into two parts. One is for n odd, taking the values 1, 3, 5 and so on, and for n even, taking the values n equal to 2, 4, 6 and so on. So when I take n odd, n equal to 1, I get that y3 0. Look at what we get, putting n equal to 1, it's 1 square plus m square into y1 0. What is y1 0? We have already calculated, putting this value y1 0 over here, this minus m into 1 square plus m square into e to the power m pi by 2. This is the value y3 0. Next you put n equal to 3. So 3 plus 2 5, I get the value y5 0 as 3 square plus m square into y3 0. y3 0 I have just calculated, I put this value over here, this will become minus m, writing this 1 square plus m square into this 3 square plus m square into e to the power m pi by 2. This is the value. And by symmetry, if you look at, if I try to write down again the value yn 0, can you think what is this? Minus m is repeating with every term, so here also it's minus m. Next term is 1 square plus m square. Next term is 3 square plus m square. And this will go up to what? This will go up to n minus 2 square plus m square. N minus 2 square plus m square. Similar for n even, it's n equal to 2 I put, this is y4 0 equal to n equal to 2 page 2 square plus m square, y2 0. And y2 0 we have already calculated, this is m square e to the power m pi by 2. So it's m square 2 square plus m square into e to the power m pi by 2. Yeah. Similar, I put n equal to 4, so I get the value y6 0, and this is 4 square plus m square into y4 0. Putting this value y4 0, so this is m square 2 square plus m square 4 square plus m square into e to the power m pi by 2. This is the value. Clear? And similar, I can write down the value yn 0 by symmetry. This is m square, this 2 square plus m square, 4 square plus m square, and this is also going up to n minus 2 square plus m square into e to the power m pi by 2. So this is the value for yn 0 for n odd and n even. Yeah. So this is the application of Leibniz theorem and how to get the value of nth derivative at x equal to 0. And that's all for today lecture.